pulse width modulation is a good technique to communicate over pulse only channels, and especially if the channel supports only 2 level or if it is non-linear. It's used to communicate analog signals across these pulse only channels. So here we will look at a pulse width modulator circuit and a demodulator circuit using the KiCad electronic circuits simulator and schematic capture tool. So as an overview, I have a 555 here to generate a Sawtooth waveform which is fed into a comparator's negative input, and at the positive input I am feeding the actual analog signal itself. Okay, and the output of the comparator will be the PWM signal that we are interested in. This can be transmitted over long distance over a pulse only channel, and then as a demodulator I am using a very simple technique of an RC filter. Okay, so we have 3 components which we will look into the design. So the 555, which is acting as a Sawtooth generator. So I am not using the digital output or the actual output pin of the 555, but instead I am tapping the signal from this capacitor itself, which is a Sawtooth waveform. And then we have the PWM modulator, which is this comparator, and finally we have this PWM demodulator. So let's look at the design of each of these parts. Okay. So the design, overall design is for modulating signals in the range of 0 to 1 kilohertz. So the input analog signal, we are expecting it to be a signal that has a bandwidth of 1 kilohertz, which is base bandwidth, which is 0 to 1 kilohertz is the range of the frequencies that it can contain. And the carrier is at approximately 66 kilohertz. The carrier frequency is going to be determined by the passive components used around the 555 IC. So first, design of the Sawtooth generator. In order to achieve the 66 kilohertz, we fix the rise time as 10 microseconds and the fall time of the Sawtooth as 5 microseconds. So total 15 microseconds period should give us 66 kilohertz frequency. And we arbitrarily take capacitor to be this C2 capacitance to be 1 nanofarad, and this gives us so now we have to, in order to determine R1 and R2 used, we have to or we can use these 2 equations to calculate them. So from the first equation we get R2 to be 7.2 kilo ohms, and we round it to the nearest available 10% resistor or 5% resistor, which will be 6.8 kilo ohms. Similar calculation for in the second equation will give you R1 to be also approximately 6.8 kilohertz. So we have fixed R1 and R2 to be 6.8 kilo ohms and C2 to be 1 nanofarad. Now let's go to the design of the PWM modulator. So here the design is there is not much of a design. So a few requirements: that the source swing should be, that is, this V in should swing in the range of 1/3 VCC to 2/3 VCC in order to prevent overmodulation. So the max voltage swing should be between 1/3 VCC and 2/3 VCC if you don't want overmodulation and loss of information. This is because the sawtooth generated here has the voltage swing in this particular range. This will be between 1/3 VCC and 2/3 VCC. Okay. And then the only other design element here is this R4 or pull-up resistor. This is because the LM311 IC, comparator IC used, is an open drain or open collector type IC. Type comparator. So you need to have a pull-up if you want to drop the voltage and see a sawtooth waveform. And now the only remaining element is this demodulator. Let's see its design as well. So the demodulator, the fundamental equation is the cutoff frequency equation for this RC filter. This is the low pass filter, and for this RC low pass filter, the cutoff frequency is governed by this equation 1/2 pi RC. Okay, we are taking R3 to be 10 kilo ohm in order not to overload the modulator. So the modulator, we are using a pull-up resistor of 100 ohms. So if you look at the Thevenin equivalent circuit of this modulator side, you will see a pulsed voltage source or PWM voltage source with a series resistance or Thevenin equivalent resistance of 100 ohms. In order not to load that resistance and to cause an unnecessary voltage drop, we have to choose the resistance of the filter side at least to be 10 times that of the Thevenin equivalent resistance. So to be on the safe side, I am taking it to be at 10K, which is 100 times that of the Thevenin equivalent resistance. So I am arbitrarily fixing this to be 10K. This R3 I am fixing to be 10K, and then I have earlier said that the design parameter is to have modulating signals in the range of 0 to 1 kilohertz. So I am going to keep a cutoff frequency of 1.5 kilohertz for this filter. And applying FC and R3 to this equation, I can find out C1, and I find C1 to be 10 nanofarad. So I fix 10 nanofarad here and 10K here. Okay. So all the passives are now designed. Now let's see the various active components here and its specification. So I have a VCC source here, and the SPICE model is basically for as a DC source of 10 volts. So this will be the VCC supply, and it will be fixed at 10 volts. Okay. And then I have a modulating signal source which provides a sine wave with DC offset of 5 volt, which is half of VCC, and then sine wave with a 1 volt amplitude. So the signal will vary from 4 volts to 6 volts, and it will have a frequency of 1 kilohertz. So this will satisfy this offset plus this amplitude condition will satisfy that the modulating signal has to vary in the range of 1/3 VCC to 2/3 VCC. Okay, so this entire signal is within 1/3 VCC and 2/3 VCC. Okay, so that is how the sources are configured. And then the 555. So in KiCad you will have to add a spice model for each of these components that you are adding. So I have obtained a 555 model from the internet, and I am using that one. I am selecting sub-circuit here, and the only model that is in that particular file is this TLC 555, which is good enough representation of the commercially available 555 IC, and I am using that as it is. And for the comparator, again I am using an LM311 library that is obtained from the internet. Same, the only model that is available in that file is LM311, and it's a sub-circuit type. So this is the content of that file, and it's a sub-circuit type. But unlike the model that the symbol that is shown here, the simulated the spice model doesn't have so many pins, so we will have to see how the pin mapping is done. Let's see that. So 1 is supposed to be the non-inverting input. So for the model, the first pin has to be a non-inverting input. But if you look at this diagram, you can see that the non-inverting input is pin number 2. So I'll have to specify the order of the order of how these pin numbers are mapping to this order, and that I have to specify here. I have to tick this alternate modes node sequence, and then the second pin is the non-inverting input. Next comes the inverting input, which is the third pin here, and the next is the positive power supply, which is the 8th pin, specifying that also, and the negative power supply, which is 4th pin, and open collector output, which is the 7th pin, and the output ground, which is this ground pin, which is 1. So I am specifying all those pins that are or I am mapping these package pins to pins that are used by the model, or that are modeled in this spice model. Okay. In addition, I am giving two spice directives here. First is an initial condition, which is we will be using a transient analysis, and for that some of these capacitors and floating nodes you will have to give an initial condition, or if you don't do it, the simulator may start with some random value, and you may not be able to observe that converged value within the time that you are going to simulate. So it takes some time to compute the, say, 3 milliseconds worth of simulation data. So within that 3 millisecond time, you may not observe the circuit settling into the steady state if you don't provide the initial conditions correctly. Okay. So I am setting these two nodes. So I am setting an initial condition at this node, which I am naming as SAW for the Sawtooth output comes there. So voltage at Sawtooth node should be 0 initially, and then another node I am setting, which is this CV, okay. And that should be the within 555 there is a voltage divider circuit, and 2/3 VCC point is the is supposed to be connected to the CV pin, and therefore I am giving initial condition at CV pin to be 6.66 volts. And that's the first directive, the initial condition directive. This is required especially for this node, because otherwise the simulation may not settle or within a reasonable amount of time. And then I have the simulation directive, that I need a transient simulation with 10 microsecond steps for 3 milliseconds or until the stop time is 3 millisecond and the start time is 1 millisecond. So I'll give the initial 1 millisecond for some settling up of the circuit, and then from 1 millisecond to 3 milliseconds I'll collect the data with 10 microsecond interval. Okay, if the simulator sees that higher granularity is needed for accuracy, then the simulator will automatically take that. Okay, and so I am marking, or I am labeling some of the nodes. One is this CV node and the other is this SAW node, both for this initial condition setup. And then the PWM output node, the VIN node where the modulating signal is provided, the PWM output node, which is the VPWM, and then the demodulated output. So I am labeling all these nets so that it will be easy for me to show you these waveforms in the post simulation waveform viewer. Okay, so tools, simulator, and if I take the settings, the transient analysis is already set up with the parameters that I have provided in the .trans simulator directive here. So using this specification, it has already populated. Okay, and then I just need to run the simulation. So it's computing successive stepping through time, and it is computing the waveforms. Okay, the computation is done. So this icon has changed its color. Now I have to select the signals that I want to observe. So I take this probe, and then I am going to probe this Sawtooth waveform, the input waveform, the PWM waveform, and the demodulated waveform. Okay, so I have all those waveforms available here. So the green one is the sinusoidal input signal, and the red one is the Sawtooth waveform. The blue one is the PWM signal, and the yellow one is the demodulated signal. Okay, so you can see that these demodulated signal tracks the input signal with a slight phase shift, but it does track the input signal, and there are some high frequency components still left in the signal, in the output signal, because we are using just a first order RC filter. If we go for higher order filters, like an LC filter, we can get rid of more of the higher frequency or the carrier frequency components. And let's look at the PWM signal itself over half cycle. So here, when the modulating the input signal, the green one is at a higher voltage, towards a higher voltage, you can see that the duty cycle is large, and as it reaches the trough, you can see that the duty cycle is very low. So effectively we are getting constant frequency PWM itself. Okay, so with that we end the presentation on PWM, modulation and demodulation.